So we've just loaded in this pre-built model of SIR agent-based calibration. And this model will follow us through our discussion of sensitivity analysis and dealing with stochastics, particularly for this topic of running what are called Monte Carlo ensembles, running the model again and again and again and again with different random number seeds, with different sort of initial, trajectories of the random numbers generated. So we can examine the impact of uncertainty associated with model stochastics or uncertainty associated with model parameters. And we're going to see how we could use some of AnyLogic's built-in tools to give us an appreciation for just how big those uncertainties are, to which parameters it's particularly sensitive. The second purpose for which we're going to use this model is a purpose that some of you are encountering as important for your projects, and that is to actually try to match up the model results on the one hand with empirical data on the other, to try to get the model runs. Okay, that's not going to occur on yours. It's because I made a change to this this past summer and didn't change it back. Trying to match up the model runs on the one hand with empirical data as closely as possible. So we're adjusting parameters there to best match data from the real world about a situation. So we can try to arrive at parameter estimates that give us a picture from what the model shows that's as consistent as possible with what real world shows. And we're going to talk about these in quite some detail. What both of these have in common is the fact that we have a situation where the model is going to be running many, many times over and over and over again. It's actually this one I meant to run. Over and over and over again with different, with a so-called Monte Carlo ensemble. We're running it over and over again with different random number seeds, and we're seeing consequences of that. Sometimes we're also further changing parameter values. But for all of these cases, we're going to be breaking out of the model we've used thus far. Thus far, we've had a model coupled with an experiment, a scenario where we run the model with some assumptions, and we get some results. And that's all fine and good, but we've been running it a single time. And sometimes, ladies and gentlemen, a single time isn't good enough. Why might that be? Why might it not be enough to just run the model one single time and declare victory and assume that we've seen the output from the model? Let me ask this. In a system dynamics model, such as we examined until recently, was one run, for a given set of parameters, is one run enough?
Yes.
Why is that?
There's no stochastics.
There's no stochastics. It's deterministic. We do that, the differential equations are well defined, they give us a precise trajectory, and we're done. Now, I'm actually downplaying the flexibility of system dynamics. There are system dynamics models which incorporate stochastics. There are system dynamics models where you can say the number of people going along this flow is a draw from a Bernoulli distribution with such and such parameters. You can do that in AnyLogic, you can do it in other packages, but it's comparatively rare. One of the real virtues of system dynamics models is that we can analyze them formally. Another virtue is that that often we find it easier to work with a deterministic model. And for a lot of these reasons, when we're dealing with system dynamics models, we're often dealing with deterministic models, models that produce a well-defined output. For a given set of parameters, you get a single trajectory output for a given variable. But for agent-based models, we don't have that situation. So let's go up here and click on simulation. Click on Monte Carlo histogram 2D here. And if we scroll down, I want to make sure mine is consistent with yours. If we scroll down here, Monte Carlo 2D histogram, we will see that there's a set of parameters listed, and I'd like to change them all in this type area to fixed. Okay, so we set it to be fixed here. And what does yours say for this? I just want to keep mine in sync with yours. For average illness duration, what does it give? Is it 10 or something like that? Are people not seeing this? 15? Okay, thank you. So we will change this for now to 15. Okay?
So when this has like the parameter, then these like something that says expression, but it doesn't have
Only the expression, you don't have the type.
value.
It's still click on freeform parameters.
Up here. So, is this what you see? Oh, you know what? It's this thing. Okay, this is a bug in AnyLogic. It's a known bug. And I think it has to do, you have to, okay, so freeform, this is what you see. Something like that?
Yeah.
Is it not? Yeah, we identified this to them a couple months ago, but they got this is the older version of AnyLogic. I think they fixed it in the latest version. Okay, so be aware that you can't just click on these. Look at that. Software engineers, this got through testing. So you have to double click on it. Okay, so these expressions are shown. So if we run this model, let's run it here. You'll notice it's saying number of runs 100. So we're going to run it with this certain set of assumptions, fixed assumptions about these parameters. Each of these listed as a parameter in the model: average illness duration, contact rate, infection probability, total population. Each is a parameter in this model that you'll recognize here. This is a model we've seen before with infection. So if we run this, we run these so-called 100 replications. A common term is 100 realizations of this model. Each of those realizations, like we're drawing a particular random number seed and we're running the model with that and getting some output. And what you'll see is not one trajectory. It's actually and you could probably see it on your computers more clearly than on the screen. But you'll see kind of some fuzziness around here. Do you see that? And and there's actually a line down here. Do you see that? Yeah. So from whence does this fuzziness come? What is this fuzziness indicating? Can anyone tell me? Why do we see this this fuzziness? Oh, this doesn't work that well. Why do we see that fuzziness?
Simulation doesn't run the exact same every time.
Yeah, so sometimes we're getting more runs, sometimes we're getting fewer runs excuse me, number of people infected, some runs are getting fewer values. This shows, I should have noted here, x-axis, time, y-axis, number of people infected within this model. Each person is associated with this state chart, and yet we're seeing, as we run this out, sometimes there's almost nobody infected at, say, time 20. Sometimes there's more people. The darker it is, the more cases have fallen into that bin. This is what's called the Monte Carlo 2D histogram. Okay? It's a two-dimensional histogram, ladies and gentlemen, in the sense that here, this space, with, again, time on the x-axis, number of cases infected on the y-axis, it's divided to a set of bins. It's divided into these little rectangles, each of which accumulates a count of trajectories that have fallen in that little bin, that have gone through that place on the screen. And the darker it is, the more trajectories have gone through that. The lighter it is, the fewer. And a couple of things will stand out at you. First of all, a large portion of this is totally white. What does that mean? What does it mean that a large portion of this is all white? Yeah, there's no trajectories that go out here. There's a lot of regularity, in short. There's a lot of order to this. We're not just getting dots thrown down at random over the screen. There's a lot of regularity, but there's some variability too. There's variability about some mean, to be sure. There's kind of this, and I don't know how well you can see it from where you are, but maybe better on your screen. There's kind of this central ridge, and then there's kind of a fringe around that. Do you see that? Yeah. Oh, okay. That's most interesting. Okay, so the question is, do people see a fringe on this? Okay, so what we want to do, Braden, is that right? So we want to do freeform here. Double click on this. There you go. Freeform. Make sure, folks. So Braden pointed out on his. He wasn't seeing this. If you're not seeing it, if you go to Monte Carlo 2D histogram here, you will see that there's a. This should be highlight. This should be active, and make sure you double click on freeform. The risk is if you're like this, like this, and you click here, it won't. It's actually still invaried in range. So you got to double click on. Make sure number of runs is shown, and then it will actually run it 100 times when you run it. It's running it 100 times over and showing this, and you should see this kind of fringe around this central point. You see that? Okay, so that's variability. Sometimes the number of people is higher, sometimes it's lower for infected. And again, we're keeping track of the number of trajectories that pass through a given point here. And you'll notice there's also some along the bottom. It's not merely a unimodal distribution centered around some point. There are some that fall at the very bottom of this area, which indicates almost no people infected. And then there's a broad space between them. Why do we get that sort of bimodality? With what is that associated often? A situation which can either turn out this way or turn out very different, but very little in between. We've actually seen that for a certain type of system before. And what sort of system is it? Well, I drew it on this board. It's standing in front of you about a month ago when I had 2 good feet to my credit. And I argued that for a certain class of systems, you could get kind of different basins of attraction, where one area, for example, went to one solution, another area went to another solution. This isn't quite that case, but it's got something similar. What sort of system can exhibit this kind of different basins of attraction, a situation where like a software project can go really, really well, be really thriving, high morale, losing few people are able to have stayed there for a long time, they can keep a lot in their heads, it's pretty lightweight documentation, you have a really good relationship with the client, it's high quality, you're able to deliver things on time, versus a situation where the same team, in a situation where you have an adverse managerial decisions early on, is constantly going from fire to fire. They never have time to do effective risk management, and therefore they're always getting new emergencies coming up. They don't have time to do proper quality assurance. The client's always disappointed in quality. They're always losing people because people don't feel good working with a really lousy code base. There's heavy documentation because people are going out the door in a revolving door sort of way. You can get these 2 very different opposite extremes in what sort of systems? Okay, hangman. First letter is G. Okay.
Non-linear.
Non-linear. Thank you. Okay. It's a non-linear system. That's when you can get these sort of very different situations going on with lock-in effects. It goes into one and stays there, goes into another and stays there. And certainly you can very easily get these very different trajectories going on while it's happening. So one where it just doesn't take off at all, and one where it takes off and falls down. And an outbreak occurs. You may remember when we studied with system dynamics infection spread models, You could get parameters where the infection never took off at all, it petered out, and some where it took off. There it was deterministic, depending on the values of parameters. Here there's some stochastics involved too. Ladies and gentlemen, so here we have this 2D histogram, and if you right click on this thing and you do copy all, and then you go down and you come over here and you call up, for example, if you have Excel or if you have another spreadsheet program, you can paste in. You'll actually see the counts. You'll actually see the counts behind here. This is indicating what the bins are. So there's one bin associated with counting the number of trajectories that from time 0 to 2.5 fall between 7,800 and 8,000. There's another bin for the next larger amount of times that count the number that fall in those areas. This is a two-dimensional histogram. We have this binning along the x-axis and y-axis, and each cell here denotes one bin defined by a certain time period on the x-axis and a certain value in the number of people affected. Does that make sense? So we're seeing some variability, ladies and gentlemen. And from whence does this variability come? If we consider our model here, if we consider this model, why do we see this variability? I mean, why are we seeing variability in it? What at a concrete level is variable within this model? Okay, yeah, rates, great. So Braden spotted that, if it was Braden who spoke up there, Braden spotted the fact that we have these rate transitions. They're indicated by the icon. So even before we go and poke around what sort of network it is, or you know, to whom exactly they send a message, we know, for example, recovery is almost certainly occurring in a stochastic way. It's associated with the rate transition, a chance per unit time. And that's associated with what sort of distribution for how long you spend in the infectious state. If you have a fixed chance per unit time for recovering, what sort of distribution is it? What's the distribution associated with how long you remain in an infectious state? That's associated with what sort of distribution? Normal is a good guess because that's a very common distribution when you add up a lot of things. But in this case, it's not a normal. It's what sort of distribution? If you have a certain chance per unit time of leaving it, what's the probability of remaining for time at least t look like? Or the probability of leaving in a given sort of given period of time t? It is Poisson. It's exponentially distributed. Where have we seen this before? This is our old friend. At least it's my friend. I'm hoping maybe it's your enemy. You know, I don't know. It's my friend, and I'll stand up for it. So where have we seen this before? This e to the minus alpha t.
Scale-free networks.
Okay, we saw it in scale. Actually, we saw in scale-free networks something like a certain value k, the number of connections to the minus gamma or something like that. So that was a power law where k is sort of the value of interest. But where have we saw that? This is associated with a process that's memoryless. There's no memory. There's a certain chance per unit time of leaving. No matter how long you've been there, you have the same chance per unit. Where do we see that first? Does anyone remember? It was with oh man, imagine what's going to happen after break. I have to start again. Welcome to class. Folks will run out of here. Okay, maybe I can get my two good legs back. So yeah, it's a first order delay. Remember that? Remember that in time immemorial? Alpha, chance for alpha, this is x. We had alpha times x. The formula here. Hopefully your memory fills in where the marker can't. and this is associated with e to the minus alpha t. Remember that? So we see that same situation. Here you have a certain chance per unit time of leaving, and so it is with this sort of transition. Okay, so that transition is stochastic. When it occurs, it's stochastic. It draws a value from this probability distribution, which is actually, I think it's 1 over alpha times this is the actual is the actual value here. Excuse me. It's I should be careful here. It's either alpha times this or 1 over alpha, because when we integrate that, this has got to cancel, and then I think alpha times it. In any case, there's a probability distribution proportional to e to the minus alpha t, and basically the timing of this value by which you go from infectious to recovered is drawn from that probability distribution. What else is stochastic here? Can you reason me that? What else? Well, if we start looking here, I see another one that's uncertain. When you send messages out, you send infection to a random person in the whole network. That's also stochastic, to whom you send that. Maybe sometimes, by the luck of the draw, the same person is being bombarded with multiple messages. They've already gotten infected once, they're not going to get infected multiple times. Those messages fall on stony ground. All of these things are within the realm of stochastic possibilities. So sometimes, by the luck of the draw, more people get infected early, sometimes few. Sometimes nobody will get infected by that early case. That, ladies and gentlemen, is why we see some stochastics. There's stochastics associated with this model. Now, for some models, these stochastics may be more pronounced. For example, we could go up to main here. Let's go down main. And you could go down and you can declare a different network type. We could declare, for example, a scale-free network. And we could run the model again, and we'd probably see a somewhat different distribution associated with its variability. Here we are having the network itself have an additional sort of amount of uncertainty, and okay, that's interesting. I would have expected it to be displaying this, but I'm not seeing. Here we go. Okay, it's just very slow. Looks like there's something else running. But we are seeing, for example, on that particular trajectory, nothing took off. Now we're seeing a larger number take off, and we might see greater variability associated with this, because there's now this also uncertainty about to whom is connected with whom within this model. So in short, we have variability from realization to realization due to stochastics within the model. Does that make sense? And in order to deal with this variability, in order to come up with a robust understanding of what this model does, what its behavior is, we can't just settle for a single run of the model. That will be based on, it could be influenced by the fluke of the situation, just the happenstance of what happened to occur by the roll of the dice in that run of the model. Instead, to develop confidence that our understanding is robust, we run the model several times over, often hundreds of times, sometimes thousands of times, at least dozens of times. And we examine the variability and the results. We deal with stochastics by a process known as Monte Carlo ensembles, which means running the model again and again and again and again with different random number seeds. Okay? Monte Carlo techniques can be found in many areas of statistics, mathematics, and computer science, and this is one area in the use of dynamic simulations where you have stochastics. You'll essentially roll the dice many, many, many times as to how the model behaves to get a sense of the variability in its behavior. Great. So that's examining the outcome of the model. with this Monte Carlo ensemble lens, this lens of running it many times. We talk about many realizations of the model.
Sorry.
Yeah.
Is there a general rule for how many times you would do a run, or how many runs you would do?
Yeah, and I'm going to talk about that in just a minute here. There's no general rule for certain subtle issues associated with it. And in some areas, such as health economics, there's a lot of, people spend a lot of time wondering, for example, if I run this model many times over, should those runs be associated with just the stochastics over time of the model? Or should we, in other words, should we run them all with the same network? Or should we be generating different networks for each of them and also have it sort of vary as to what happens over time? Do we control, as it were, for network variation and only have it vary in the stochastics over time, or do we throw in network variability as part of the run? And that's a topic of considerable interest for certain types of analysis, because they want to do a very precise kind of understanding of where the variability is coming from. So let's talk about it. Stochastic processes are very common in the real world, and often our models incorporate stochastics. The key thing here is that what's treated as stochastic in one model may be treated and unpacked into deterministic factors in another model. Within a more general model, we might treat aspects of individual behavior as stochastic. We might treat aspects of the environment as stochastic, whereas in another model, those become points of interest, and we actually try to represent them in a more deterministic fashion. So this issue of the boundary between what's stochastic and deterministic is often less a matter of the real nature of the world and a matter of our modeling approximates. We can do lots of things. If we can't simulate it well, we approximate it as stochastic. When I say stochastic, I mean there's randomness over time. Okay? So we'll do things like simulate rainfall over time as being drawn from some stochastic process. It'll be drawn from as random variables over time. Oil prices, economic growth, stock market fluctuations. In other cases, we might have a strong interest in simulating the weather, in which case we'll have a model where it's not treated as stochastic but deterministic. So that boundary, what do we kind of incorporate deterministically, what do we incorporate stochastically, will shift from model to model and model. It's not something we say that phenomena out there in the world is stochastic for the most part. There are some points where that argument breaks down. For example, quantum phenomena. I'm led to understand by those in the physics domain that as best we understand it, you can't have a totally deterministic simulation of exactly when a subatomic when a certain atom will decay, for example, will undergo electron emission or something along those lines. So there may be processes at a very microscopic level, a quantum level, which are inherently stochastic. But for the most part, stochastics in a model represent the scope of the model. What we exclude from the model, we treat stochastically when it's convenient. So within our models in AnyLogic, for example, as one platform, we very commonly have stochastics for agent-based models and discrete event models. There, the uncertainty plays often a key role. And so here we run the model many, many times, okay? So here we're drawing repeated samples from distributions, and we simulate out the model with different random number assumptions. So here we're accumulating this histogram 2D data chart. The reason for that is, why do we use one of these 2D histograms? Well, if we drew out over time, if we were to draw out when we run this model, over time, again and again and again, each trajectory, you'll get very messy. It'll be just line over line after over line, and we couldn't really see how many lines are there. It looks really dark, but you can't really tell how many are on top of each other. And in general, it would be hard to see how many things fall in different areas. And so counting the number of times a given bin is occupied turns out to give a lot of insight. It doesn't keep all the information. It doesn't tell you where the trajectory went next after a bin. If this is dark, it doesn't say where the trajectory is going, this way or this way, this way or straight over or almost straight down. But it captures a lot of information in it. Okay, so I'm not going to dwell on this much, this 2D histogram, except to note that it's a very valuable mechanism. Okay, so we're analyzing this now. There's a little bit of information about how this works at a plumbing level that you should recognize. And for those of you pursuing projects, you might really want to pay attention to my next 5 minutes of comments. So what's going on here at a plumbing level with this model? Well, one thing that should be obvious to you is that we're beyond the point of having the model simulated a single time so that we run main is done, and our simulation is done. That paradigm is out the window. Instead, this experiment is running main many times. It's running it again and again and again and again with different random number seeds. And in order to enable that, there's a set of mechanisms in these properties of this experiment in AnyLogic. This is a special type of experiment in AnyLogic. And if we go and we scroll down here, you'll find, in addition to saying that this depends on a random seed, which is something we haven't emphasized before, but you can either say, I want my run to always reproduce exactly the same results by having a so-called fixed seed, so it has the same sequence of pseudo-random numbers, assuming it's the same model. We can also say it's a random seed. And here, you'll notice down at the bottom, this is where the fox will show its tail. Okay? So let's go take a look at the mechanisms here. What's going on is that this model is going to be running main many, many times, and it's actually going to be retrieving information after each run so that it can display it in the experiment. Okay? Let me just illustrate this. You'll notice when I'm running this model, when you're running it here, and I do run, what am I actually seeing here, ladies and gentlemen? What canvas stands before me? Is that main? No, it's the experiment. This is the experiment showing for me. I'm running the experiment. Normally, if I wanted to see main, what I would do is I would run a simulation, for example, here, and I'd say run, and it would actually show me the canvas for main, and it's doing it very slowly here. But you remember there's this button we would push, and it would show us the model running like this. Do you remember that? And in this case, it's not a particularly engaging example. But what this is showing here is the experiment. And if we press run 100 replications, it's actually still showing us the experiment. It's just running the model from main, grabbing information from it, and displaying it on this chart here that stands before us. Let's go see how that process works. How is it that it runs this with a certain set of assumptions, it grabs the values out, and it plots it on here? Let's go see how that works, okay? And this will be particularly of importance to those pursuing projects. So if you go to this Monte Carlo 2D histogram and you go down to the bottom, you'll see, first of all, there's a bit of work to be done when the experiment first runs, okay? Just before it's actually set to run, it will set up some data. First of all, it's going to clear out any data that's already accumulated from main, in case it was run earlier, and we were just running it again. It clears it out, and then you'll notice it clears out all this information shown in that 2D histogram. But this is the key thing. So it basically initializes some stuff here so we don't see cruft from an earlier run. So if we, for example, if we were to run this twice in a row, if I were to do this run 100 and then I were to finish it up and then I were to press this again, we don't want to see stuff from the earlier run. Okay, so it just clears cruft up from the beginning there. And then you notice this is the key thing. Ladies and gentlemen, after each simulation run, it's actually grabbing some information from main. That's what this root refers to. It is to main that root refers, and the hint will be over here in that little bulb here. The root active object class, which is in this case main. So what it's doing is it's grabbing from main something. And what is this something? It's a data set. It's a construct that AnyLogic provides to accumulate data in main. We'll go see where that's accumulated in just a minute. But basically, after main is done running, main is going to be recycled. It's going to run main many, many times. So it salvages. It goes and grabs from main this data that main has accumulated during its run, and it sticks it in a data set to put it in a bin fashion on that chart we saw earlier. Moreover, it's going to add in to a certain histogram. I guess yours doesn't have this. Is that right?
We don't have.
Okay. So we could add that. Quite easily. But this basically reads out a certain variable from main and puts it into a histogram here in the experiment. So these things are in the experiment. These are constructs in the experiment. It's reading out data from main and accumulating it in these variables in the experiment. Let's go see where this infectious DS comes from. So there's little mystery here. Let's go to main. Let's go down main. And here we'll see this infectious DS. This is a data set, and this data set is again a construct in AnyLogic, and we can tell it sample from the number of infectious individuals every 2 time steps and update its data automatically. So it's going to go through and over time accumulate the number of people infected. So let's go see how that works. I'm going to run just this normal simulation here.
And we don't have the normal simulation.
Oh, you don't? Okay, so let's go add a normal simulation. Watch this. I'm going to delete mine. Okay. Sidyala. Okay, let's add this in. Simulation. We're going to add in the experiment. We'll just call it simulation. How did I do that? I just went new. I did experiment, and I just did the top one. Some of these might not be visible depending on your version of AnyLogic. So now there's a simulation here, and if we were to run that, what we would find is that as we run it, it's actually going to be accumulating data in this data set. So I'm waiting for it to start running here, and you'll see that it's accumulating data in this data set over time. Do you see that? So this data set is accumulating information over the course of the run, and at the end of that run, if it's running within this parameter variation experiment, it reads that value out of that data set, and it puts it into its own data set, which lives, ladies and gentlemen, in the experiment here. It lives over here in this data infectious 2D. And that data infectious 2D tells it, okay, what are the intervals? What are the bins into which it's divided? How many horizontal? How many vertical? These horizontal are the time ones. These vertical are the ones in the number of people infected. And it asks, how do you want to summarize it as well? And then this one here just depends on the data infectious 2D. So in short, ladies and gentlemen, if we're going to do this parameter variation experiment, we need to read data out of main every time we run it, salvage it, store it away so that we can present it in this experiment. That's a bit about the plumbing, so that you could create something similar. I have videos of myself building up one of these, and it's not terribly difficult, but you should realize that's the basic mechanism of how you undergo that. Maybe just to allow us to experience doing this a little bit, I'm going to delete this, ladies and gentlemen. Here, you don't have that, I think, right?
No.
You have no such no such construct. And if you go to main, you have no such construct, count cumulative infections. Is that right? So it's not there at all, right? I recognize my naming convention. I figured as much. Okay. Okay, ladies and gentlemen, I just deleted that. So let's go through that little exercise. Let's add a piece of information to be displayed in the experiment and see how we do it. Shall we not? Okay. Okay, ladies and gentlemen, so I want you to tell me now, how am I going to keep track in here? Give me one way of keeping track of how many people have ever gotten infected in this model. What will be one way? A variable. Good. Good. What might we call that variable? Count cumulative infective? Okay, something like that. Cumulative infections. Count cumulative infections. That sounds like a pretty good variable name. If don't mind if I do say so. So, ladies and gentlemen, we could drag into main a variable, call it count cumulative infections. And what sort of variable is it going to be? Is it going to be a double? Is it going to be a string? Is it going to be a person? It's going to be an integer. And what's its initial value going to be? 0. We're going to treat it as 0 to this point. Now, here's the question. What sort of process would need to increment that? Under what conditions do we know we have a new infection that has taken place? Where would we go in the model to look at the place where a new infection takes place? What is it that sort of marks the occurrence of a new infection in this model? It's what? It's in the state chart in person. That's exactly right. So I added to main this variable called count cumulative infections. Did I not? I did. It's an integer variable with an initial value of 0. Now let's go to person. And where would I go where would I go if I want to find the place where an infection occurred? Riddle me this. I'm sorry? Yeah, infection. This is the event of an infection. So I go there and I find, oh wow, someone already did this. Yeah, okay, so you're going to want to put this in the action associated with this. You're going to want to increment that variable in main. So main dot count cumulative infections plus plus. And I hope it will be second nature for most of you from computer science. It's followed by a semicolon because this is a statement. It's a command. It says do this. It's not just something to compute a value. So we are saying the value of count cumulative infections in main, add 1 to it. To whatever value it has, make it 1 more. Does that make sense? Okay. So we're incrementing that there. Great. We just added this variable to that. So you should be able to run your model now. Maybe run it with that simulation we added earlier. We did this new, remember, experiment simulation before.
What about the other transition just inside that infectious kind?
Okay, so that's a good question. What about this transition? Do we need an additional bit of logic there? Why not? So Tanner is correct in indicating not. What, anyone want to say?
If it does work, then it'll show up in the top infection.
Yeah, exactly. So this is a bit of a point that can be can take potentially a bit of time to fully absorb. Why is it we don't have to put it there? Well, if someone's infected, if the receiving side is infected, they'll be going through this transition from susceptible to infection. They'll be the ones infected. This contact, this occurrence of this so-called contact, that's actually not definitely infecting someone. Why is that? Why do I say that? It's not definitely infecting someone. It's sending a message, but who could get that message?
An already infected person?
Yeah, an already infected person, or a recovered person could. So just because it's sending an infection message, it's a little bit misleading. Really, this should say exposed, or it should say, exposed to infection or something like that. Because it's actually not definitely getting infected. It's sending a message to a neighbor or to a random person in the network. This shouldn't, when I did the scale-free network, I should have changed this to be random connected. But the point is that it's not the case that here someone else is getting infected. And we only have to, even if it were the case someone was getting infected, it would be perfectly good to handle it here. Because there's a person getting infected here. This is the place where they transition from a susceptible to infectious state. So from a point of view of clarity, I say it better belongs here. Does that make sense?
Yeah, right.
Okay. Okay, so ladies and gentlemen, we put this bit of code in there. Any questions on that? Okay, so you should be able to run this thing now under simulation. Oh, okay, it's okay. It's exhibiting displeasure. So let me go find out. Oh, okay, that's because I didn't clean up my work here. Okay, fine. We'll go and pardon me while I just make mine totally compatible with yours, because I left something in there that you folks won't have this thing here. Okay, we'll come to that. Okay, so you should be able to run this simulation. It was refusing to build it for me. Oh, it's still causing, okay, what's the problem here? Count, oh, yeah, okay, fine. And it's still causing a problem, so what's the big deal? Oh, there we go. Okay. There's a chart that depends on that. Well, we'll get to this. Okay, fine. Go away. Okay, so in short, we should be able to run this, and you should be able to see that variable increment over time. Should you not? You should. Okay, so over time, there should be, this count cumulative infection should be incremented, right? You could click on it, you could go see a little graph of it. Hey, I'm not sure why it's not allowing me to do, there it is. This is the count of people cumulatively infected over time, and if we ran it, we'd see it sort of goes up to 10,000. Okay, ladies and gentlemen, so we just added that variable. How are we going to now, I'd like to create a histogram of that in this experiment. This experiment's going to run the model many, many times. How are we going to create a histogram of this? By the way, this little exercise will be maybe helpful for you in problem set 3. It'll very likely be helpful for you in a coming problem set. So very similar to the issues with calibration. So how are we going to have this thing display? Suppose we want to display a histogram of across different runs of the model, different particular realizations of the model, running it with different random number seeds. How would we get it to show the different number of people infected cumulatively? Anyone? Okay, yeah, so we're going to go down to analysis, the analysis palette, and we're going to go call up here a histogram chart first, and we want a chart, but in order to get the chart, we're going to need to add a histogram data object, something that kind of holds the data and has binned it into bins. So I'm going to drag in a histogram data structure here called cumulative infections histogram data. Okay? Okay. Cumulative infections histogram data. That was this histogram data object here. Okay? Okay, now, the cumulative infections histogram data, you'll see it can specify various things, like the number of intervals, etc. We're going to leave those unchanged. Okay? And we're going to set this chart, ladies and gentlemen, to depend on this histogram data object. So This chart is, we'll call it cumulative infections histogram chart. Okay? Okay. And this chart is going to refer for its histogram data object to what? Folks, so what is it going to refer? Yeah, to this histogram data object we just added. So in short, in order to display this thing, we need to add a chart, but we need to have sort of a data set that accumulates, or data object that accumulates the data into the bins. And that will be called this histogram data object. There are two different things. This is a histogram data object, and the other is a histogram chart. Okay? And we'll call this cumulative people infected, cumulative infections. Okay, cumulative infections. Great. At end of run. Great. Okay. So that's our cumulative. That's our histogram. It's depending on this data object, and this data object is going to depend on what? Where is this data object going to get its data from? To get the cumulative count of infections. From whence will that information come? From? It'll be coming from, so where does this thing live? This thing lives in the experiment. But from where is that information going to come? From main. Okay, so to see that, remember we go down in the experiment, we scroll down to the bottom, and we need to get that information in. So before each experiment run, we're going to reset this cumulative histograms data. We're going to do a reset on it. Okay? Reset it. That's step one. Before each experiment, we're going to reset this data. Just in case there was something there we ran earlier, we're going to get rid of it. Clear it out. Start with a fresh slate. Okay? Are people following along? Okay. Next, after the simulation run, this is where, what is this doing here? Ladies and gentlemen, what's going on here? It's rescuing data from main and it's storing it here. So what would I need to do now for the coup de grace, the final step? We have to add the data to this histogram data object. So cumulative infections histogram data dot add, and what value do we add? Yeah, the root dot what? Root means main, so it's a reference to main. And what value in main? Count cumulative infections. That's what we want to add. Let me put it up on the big screen. This is what we want to add. Ooh. That's what we want to do. We want to add in to our histogram data object a value read from the main class at the end of the run. This is occurring at the end of the run. It's going to grab out this value from that variable we just added, right? This is the variable we added just a few minutes ago as I sat before you. And we're going to add that into the histogram data object. And the chart will take care of displaying what's ever in the histogram data object. So shall we run it, ladies and gentlemen? Does anyone want this up here longer? Anyone want that still up? Going once? Going twice? Okay. Okay, here we go. We're going to run this thing. Where's our histogram data object? Whither does it live? Okay, yeah, it's over to the right-hand side. By the way, the reason this is slow is because it's still set to display a scale-free network. But really, to do a scale-free network, I should be having them send not to a random person the whole network, but to their neighbor, really, to make use of that. So I'm not really taking advantage of that. Okay, so ladies and gentlemen, here it's running this thing, and what you're seeing is very repeatedly right now, 10,000 people infected at the end of the run. We could right-click on this, do copy all, go paste in an Excel sheet, and create an Excel sheet, and we'll find so far all of them have been 10,000 in value. In general, this thing may vary between realizations, particularly as we change parameter values, which we're going to be doing next. Okay. Oh, here we go. We're already getting some. What is that telling us? Sorry? What is that telling us? If we have a histogram like that, what is that? What's the implication of that? Speak, youths. Okay, two very different outcomes. Some outcomes yielded a large number of infectives, some not at all. Now, if we had gone and actually done due diligence, and if there's anyone who wants to try this, you could have gone and in this contact, instead of sending to random, you could send to random connected. Alternatively, you could do at the front here, send to random neighbor, and that would be another alternative, and then you just have to specify this message, and then you don't have to deal with this constant, something like that. Now, if you were to do that, now you're sending just to neighbors in the network, in the scale-free network, and we might expect some variability that's even more significant, both in terms of the progress and in terms of the oh, look at that! Oh, that looks really interesting. Wow. Okay. Well, I'm interested to see. So let's go see what went wrong here. Oh, okay. Console. There we go. Where's the console? Oh, there it is. Okay. Experiment. Error in the model. Okay, that's really interesting. There's something occurring there which I didn't anticipate, and I'm not quite sure why. I'm going to run it with a single realization, and we'll see what happens. So I would have expected that to be. Oh, of course. Sorry, folks, I screwed up. This should not be to random neighbor. What did I do? Rookie mistake. Random connected. Sorry. What's random neighbor? That's a neighbor in space, and I don't have them in a network in a neighborhood right now. I don't have them in a spatial layout. That's why you can't say send a random neighbor because there's no neighbors. Send a random connected, a random person to whom I'm connected. Okay. So with this, there'll be more variability likely than we've seen in the previous one, because sometimes it will be snuffed out more easily, and sometimes more of an outbreak may occur. So anyway, what we've just seen is how to add a variable in. We've seen how to summarize the results of that variable in a histogram, and we've seen also how to change a minor thing like the nature of the network that's used. Okay, so any questions on what you've seen thus far with respect to stochastics? Yes?
How do you move your chart over?
Right-click.
Yeah, it doesn't work.
Does it work? Okay, try this. Let's try this. Okay. So if you go click on this and you scroll down, there should be something that's called in the window area, enable panning. Do you see that? It's in the window area of the model, under the properties section of the experiment. Is that checked right now?
No.
Okay, check it. And you notice there's also an enable zoom, which would also be nice sometimes. And if you do that, that should allow you to pan around. I probably said it earlier and forgot that I had changed it, but that will let you drag around horizontally if you do that enable panning. Does that work now?
Yeah.
Yeah, okay. Okay, ladies and gentlemen.
Is there any way to change the speed right now for this kind of?
Okay, that is a great question. Another very practical question with significance. So Ibrahim just asked, is there any way to change the speed of this? And the answer is no. And the answer is no in an interesting way. This type of running of the model runs it as fast as possible. And that's significant because it's actually, what is it not showing here? It's actually not showing all the vagaries of what's on the screen in a given run of the model. It's actually doing a lot less work than it normally would, particularly if you have a model with lots of things going on visually, because it doesn't need to display every thing as the experiment. So this is actually calling, a method to run a parameter variation experiment. In general, it's going to run faster than if you ran just a regular experiment, because it's not bothering with the display of that model. And this is very useful, because if you want to run your model as fast as possible, particularly like with a large population, run it as a parameter variation experiment. It may get rid of a lot of processing time associated with displaying it. Okay? Yeah. But there's no way to change that at that speed. Okay. Any other questions? Great question. Okay. So, ladies and gentlemen, I'm going to power through some additional components here. First of all, there's several different ways to summarize within these 2D histograms the results. So to summarize this sort of thing, one way is to count the number that have fallen in a given area. Another way is to actually specify the whether we want to. So we can do it as the counts, or we can do it as what are called empirical fractiles, which or empirical quantiles, which basically summarize the fraction of runs that fall within a given band around the median. What's the median of a distribution? Who can tell me? One of the undergrads. What's a median of a distribution? Okay. Close in a way, because that's also a point of great interest. That's actually called the mode, the single most common value. Well, what's a median?
Middle.
Okay, middle in what sense? That's correct. But people talk about middle in different senses. Some could argue, well, a mean is a middle. It's the average value. It's the expected value of the distribution. But it's actually different than the mean. What does it mean by middle in this case? It is a middle in a sense. What is it?
If you line up the people,
Yeah?
it would be the middle one, I mean.
Okay. Okay, yeah, you're not paying attention to how far out they are on either side, just the number. It's the value above which 50% of the other values lie and below which 50% lie. The mean actually considers the values out there. So, if we have something like this, if we have something like points, a point over here, a point over here, and then 2 points here, and then say another point here. Where would the median lie? The middle point. It would actually lie here. Where would the mean lie? It would lie somewhere out And I'd have to think about this a bit, but it might be somewhere out here or something like that. Because it's being kind of pulled up by how far out this guy is. The median is less subject to the vagaries of how far out. It's just the point above which 50% line, below which 50% line. And it's around that point that we can compute these quantiles. And so there's this notion of showing what are called envelopes here. And I won't go into this in detail. But the basic idea is we show kind of these ranges around that median value over time that identify ranges in which 75%, for example, of all of the runs lie, or 90% of all of the runs lie. And you can think of it as a box plot. Have you folks, how many people here have seen box plots before? Okay, so when you've seen a box plot, it looks something like, and they vary a little bit in their details, but it looks something like this, right? So help me interpret what this box plot means. What's this lowest value? The lowest whisker, as it's called. What is it? Okay, it's the minimum associated with, so box plot summarizes a bunch of values in a single little sort of diagrammatic representation. So this represents so the y-axis here is the value, right? This may be summarizing 1,000 values, 1,000,000 values, 20 values. Okay, this lowest one is the minimum. What's the top one? Max. The max, good. What's this middle one? That's the median. Sometimes you'll additionally see, in the diagrammatic representations of it will differ, the mean shown also. It may show a star or something like that for where the mean is here also. But the most fundamental one is the median. What's this lower one here? The lower part of the box. Sorry? Yes, so it's the 25th percentile. In other words, 25% of the values lie below this. And this top? 75th. And that's what we're getting, that's what we can get with these empirical fractals. We can tell it to sort of draw values at this point around the median over time. Okay? And this will actually summarize it. If we cut it through here, kind of took a saw, like that, and we were to cut it through here and kind of look at it at a side, we actually see a box plot. Box plot would kind of summarize the location of this line, the values. It wouldn't be located vertically where it is up there highlighted. It's just to show that this could be summarized by a box plot. Okay? So this kind of gives us a sense, these envelopes gives us a sense in a box plot-like way of sort of the distribution. Okay, and the other one is bins, which we were looking at. Bins can capture non-monotonicity, the fact that it goes up and then down and then up and down and so on. Here, if we were to look at the bins at that point and we were to cut it through them and we were to look at it, we'd see a histogram. Maybe in 5 years when they have a 3D panel, you could see it. If you look at its side, it would look kind of like this. There's the bottom at 0, and then it rises up here, and then it goes down. It's 0 for a bit, and then it starts to rise again, and goes up, and then down in the middle, and then up, and then down, and then 0 up here. You see that? Yeah? Okay. So these are different ways of summarizing results. And these sort of results are very common when you're summarizing the results of simulations, either 2D histograms or these sort of box plot type representations. Box plots are very good to know about. You'll see them used for stock market data. You'll see them used for temperature. You'll see them used for data about like glucose levels, any number of different things which you can measure. And you can summarize a lot of data very efficiently with a box plot at a given point in time. Okay, now, one thing we haven't looked at is how many runs are we going to do? And we have a choice as to how many we can do. We chose 100 within hours without particularly thinking about it. Whoa, sorry. Without particularly thinking about it much. We chose 100 up here, free form 100. But in general, we should realize that as we increase the number of runs, our estimates of certain statistical quantities will become more precise. And I don't have time to go into this in general, in detail, but if we're trying to estimate the mean of a distribution, if we want to understand, for example, how the mean value of the results for a baseline without any change and compare it to an intervention which has some change to the situation, we invest more money, or we change the number of doctors we have or what have you. If we want to compare the outputs, the outcomes of each of those, we'll often want to do it with the mean, say. And if we're computing a mean, we're trying to estimate the mean from the output of this model. And we could run it 10 times, or we could run it 100 times, or we can run it 1,000 times. How is that going to increase the level of accuracy with which we could estimate the mean? The standard error in estimating the mean. How much do we need to increase the number of runs, say, to reduce that uncertainty about where the mean lies by a factor of 2? Can anyone say? If we run it with 10 runs, we get some mean out, but it has some level of uncertainty, or there's some variability associated with the standard error associated with it. Suppose we wanted to reduce that level of variability by a factor of 2. We're running it now with 10 runs. How many runs would we have to run? So you might think 20, but the actual answer is 40. 40. It actually varies with 1 over the square root of the number of times. So if we want to reduce it by a factor of 2, we have to run 4 times as many runs. 4 times as many. Okay? So the standard deviation associated with this estimate of mean will be the standard deviation associated with the distribution divided by the square root of the number of runs. The more and more times we run it, the better and better our estimate of the underlying mean will be. But it won't go down linearly. If we double it, it won't have it. We have to multiply it by 4. And if we do it by 16, we'll get 4 times the level of accuracy, in the sense of reduce that estimate of the mean of the distribution by 4 times. So you should be aware of this nonlinearity associated with sampling. If we want to arrive at some estimate of some median, particularly when comparing one result against another, we may have to run it many times to get the level of accuracy. Okay, so those are some comments here. I'm going to ask you to watch a video for our next class, but I just want to give you a little bit of a glimpse of it right now. And it's about this issue of sensitivity analysis, which builds directly on what we're talking about here, and in fact uses the same interface. We've been talking about uncertainty, checking about the results of the model with respect to uncertainty, with respect to one type of uncertainty, stochastic uncertainty, ladies and gentlemen. And that's running the model again and again without changing any assumptions about its parameters or the structure of the model. But in general, when we build models, we typically have imperfect understanding of the situation. We're building a model that captures, models are like thinking tools. My colleague Jeff McDonald calls them, appropriately enough, thinking prostheses. They're kind of just like a prosthetic arm or a prosthetic leg, or indeed a boot on a broken foot. They provide assistance for thinking through consistently the implications of our assumptions. And we can see how well the implications of those assumptions, when logically played out in a precise way, match up with real-world data. They help us debug our thinking, help us learn faster. But often we're dealing with a situation, ladies and gentlemen, where we have imperfect understanding of the world. We want to depict it in this model, but if we're going to draw conclusions from the model, we want to reflect the fact that we're uncertain about certain things. We want to see, for example, maybe we're uncertain about a bunch of different factors. But ladies and gentlemen, in a nonlinear model, and this may have been explored in one of your problem sets, in a nonlinear model, some of those uncertainties matter more than others. Some of those uncertainties make a big difference in terms of the outputs you care about, or in terms of your choices, and some make almost no difference. It's a pronounced feature of nonlinear models that some things you change a lot, and the output barely matters at all. It's not the bottleneck. It's not the limiting factor. It's not the thing which really makes a difference. Sometimes you change one parameter a little bit and makes a big difference in the results. And so when we're working with these models, one of the most useful things we can do is check how much do the results we see vary with our uncertainties. So we go through a type of process called sensitivity analysis. And there's many sorts of these. We can examine changing a parameter value by itself. We can examine changing two parameter values at the same time, or many parameter values at the same time, or ranges of them. We may want to change, for example, our assumptions about model structure. We say, well, suppose there was an extra link here. Suppose people could lose their immunity over time to Ebola. How would that affect our expectations of what will happen over the next year in terms of spread Ebola worldwide? Maybe scientifically we don't have a great understanding of whether people have lifelong immunity. Suppose they lose immunity after 2 years on average. Would that make a difference in terms of how it's likely to spread in coming months? That's exactly the sort of thing you can do with a structural sensitivity analysis. You add in some assumption about the loss of immunity. So, ladies and gentlemen, when we're conducting sensitivity analyses, we're often examining the impact on a model of changing our assumptions. And within the lecture I'll ask you to watch, what we're changing is a particular simple type of uncertainty, but it's the most common type we examine in practice. And that is uncertainties about parameters. And for those doing the projects, I've asked you to try to do a sensitivity analysis if you have a model. Okay? So here we're dealing with trying to examine what's the impact of changing parameters. And if you go into that model that we have open now, and I invite you to do it, even as it stands before us, you go to this experiment, ladies and gentlemen, and you go to this varied in range thing. Okay? And we change this from a type fix, so make sure you double click on that. Varied in range. You'll notice that this is now hidden. And we can change this. Let's change average illness duration to vary in a range from 5 to 25 in steps of 5. Okay?
Nate,
Yes.
What was changing before doing this?
So before I was on freeform like this,
Yeah.
and now I'm on varied in range.
So what was changing before? I mean, in a freeform.
In freeform, nothing was changing. We were doing it with fixed parameter values. We were just examining the effects of stochastics. So we weren't changing any of the assumptions about parameters. Remember that? We were just running the model again and again and again with
Just
no changes.
Getting infection.
Yeah, just the vagaries of chance of when someone happened to get infected. Here we have average illness duration, and we're changing that. Let's now also change, for example, the infection probability. Let's change that to go from a range of 0 to 1, step 0.1. Okay? So here we're changing the chance that given exposure someone will get infected to go from 0 to 1 in a step of 0.1. Now, ladies and gentlemen, we can run this out. Now, mind you, I still have, probably I should have still had that up there, 0 to 1 with step of 0.1. So what this is saying is we want to run this model again and again and again with different assumptions, on the one hand for average illness duration and on the other hand for infection probability. And we're going to examine all possible combinations of them. Okay. So,
How many times it's going to be?
well, okay. So let's run it and let's see how many times it actually does it, and then we could see. The problem is I've still got it doing this larger scale scale-free network, and that's going to take time for it to compute. So this is probably not going to be good. I'm going to change it from a scale-free network in main to something that's quicker. I'm going to change it to a no, I think I'll change it back to a small world network. Okay. So within this, I'll change it to a small world network. Here we go, with connections per agent of 20 and a neighborhood length fraction of 0.95. Okay, and I'm going to now run this, connections per agent of 20, neighborhood length fraction of 0.95, and I'm going to run it. And that will be much faster for it, because the scale-free network actually takes time for it to compute. Okay, so here we go. It's running this thing over and over again, and you'll notice it's run 3 runs, 4 runs, etc. And let's see how many it computes. Is anyone's computer going faster? Look at that. It doesn't seem to be spreading significantly. Anyone's computer going faster here? Tell me when it's finished on anyone's machine. No? Okay. The answer is it's going to run, I believe, 55 runs.
5 times the number.
So, where did that 55 come from? Anyone?
5 steps for parameters.
5 steps for this, 5, 10, 15, 20, 25, times 11 possible values for this. Okay? So it's going to run all possible combinations of them. As many runs as to take all possible combinations of that. Now, we don't have to live with that. We could actually tell it, for example, to run an arbitrary set of values by reading them from tables, but that's a frequent case. You want to examine sort of all possible values. Okay, so this is our histogram showing the different outputs across these different runs from running the model. And you can see it's quite bimodal. Some have almost none, some have quite a few, and then some pass between them. Interestingly, I can only see the small ones here. I can't really see the large ones, but we could see there are some that have large numbers. So here we're running the model many times with different parameter assumptions. Now, what's the problem with generalizing this to large number of parameters, ladies and gentlemen? Suppose I were to say, well, let's do this with 10 parameters. By the way, you notice it's finished after 55 runs. So it ran it for all possible combinations of these. Suppose I did this for 3 parameters, and I varied that third parameter by 10 times. How many runs would it do? Over 10 possible values. How many runs would it do? 550. 55 times 10. Suppose another 10 associated with a different parameter. 5,500, right? It tends to scale, it tends to exhibit what's called the curse of dimensionality. It grows very, very quickly, okay? We can deal with this. There's a combinatorial explosion. There's a combinatorial explosion. We can get a number of runs that requires a large amount of effort. And we haven't even examined the stochastic within each run. We've run this thing for different values of parameters, but within each of the values of the parameters, ladies and gentlemen, there's some uncertainty. We can introduce that here, and I appreciate your patience as I'm just finishing up here. See, in this replications area, we could say use replications. And it says replications per iteration. This 10 indicates run it 10 times for every combination of parameter values. But that can become very, very expensive in the end. So what we tend to use here is we'd like to be able to use schemes that will lower the number of combinations for us through the use of techniques known as Latin hypercubes, where we test each value of a parameter at least once, but not all combinations of them, or what's called an orthogonal array. How many people have heard of an orthogonal array before? It's used in software testing, and it's a very important technique if you want to test large possible, how your system functions with different inputs for different parameters in a software system. You want to run unit tests or tests that test system-wide behavior. So orthogonal arrays will test each pair of parameter values at least once. It doesn't guarantee all possible combinations, just that every pair of parameter values will be tested at least once. So if you have parameter A, B, and C, each of them can take on different values. It doesn't guarantee that you're going to do all possible combinations of A, B, and C, but that every possible combinations of A and B will be tested, every possible combination of B and C, and every possible combination of A and C. It turns out that's hugely less than all possible combinations of A, B, and C together, by orders of magnitude often, sometimes by stupendous amounts. So here we are simulating all possible combinations of values. Not all possible combinations, but all pairs of values. And in software testing, this is because often it's those pairwise combinations that are the problem. It's the fact that you can't run this thing on this operating system or what have you. It's not all possible combinations that reveal the problem, but just looking at a particular pair. In this sort of work, it's often the particular pair of values that causes the interesting behavior. Okay, and it turns out that there's various clever ways to generalize it. I will request that you know about Latin squares and orthogonal arrays for the sake of an exam. So please do take note of them, and you can read up on them. I know it's it's exam week for a lot of you, and I recognize that a lot of you might not have time to watch that video, but I'm trying to do a sort of high-level overview, and if you have time to watch it, great. I'm not going to require it, but do pay attention to orthogonal arrays and maybe read up on them a little bit more in Latin squares, Latin hypercubes. Okay. Okay, so we can avoid this combinatorial distribution with clever choice of our parameters. Okay, so we've seen a whirlwind tour of dealing with uncertainty, both in its stochastic form and with respect to parameters here. I'll send you a video. If you can watch it, that's great. If you can't, I understand, and I appreciate that you have exams. We will be talking about calibration next time, okay? That final process which many of you will be undertaking with your projects. So thank you very much for your patience. And if anyone wants to stay for office hours, I will be here, although I'll be sitting. Okay? Thank you.